So this next video is going to be introducing the complex plane and trig form. So now that we're dealing with complex numbers, especially with that imaginary component, those imaginary values do not exist in the real realm, okay? However, they do meet within the real realm. They do intersect, and that's going to be here at 0, 0. So we have the real axis here, which represents the A, or the real component. And then we have the imaginary axis, which is going to be this vertical axis that is perpendicular to the real axis, okay? And this will be your B value, your imaginary component, right? And these two, where this intersection happens, is called the complex plane. It's also known as the Argand diagram. So just like we call the XY plane sometimes the Cartesian plane, we also call the complex plane the Argand diagram, okay? And essentially, it's rectangular, so it's going to have some similar properties as the XY plane because you're given a horizontal component, which is your real value, and then you're given a vertical component, which is your imaginary value, okay? So if we look at this complex number, we see that it is plotted horizontally at 1, and then vertically at negative 2i. Therefore, this complex number is going to be 1 minus 2i. But since we are plotting it, we can also write it as a coordinate point. So this is our rectangular form, a plus bi. And then if we were to write it as a coordinate point, we could write 1, negative 2. You could include the I or not. We are already in the complex plane, so it's implied. So that's also going to be the same as a and b. So you can also write it as 1, negative 2i, and then this is the same as a bi. So one interesting thing that I want to look at is points plotted in the complex, for a complex number, a plus bi on the complex plane is really no different than plotting ab on the Cartesian plane. So that's what I already mentioned before. But let's start with I. If I wanted to plot I in the complex plane, you're able to get the coordinate point if you were to write out the entire complex number. So I has no real component, so that would be 0. And then the imaginary component is just 1i. So if I were to plot this, horizontally we would start at the origin, and then we would go up 1i, so we end up here. And now let's think about, let's do negative 1, okay? If I wanted to write negative 1 as a full complex number, the real component is negative 1, and then the imaginary component would be 0i. So if I wanted to plot this in the complex plane, we would travel horizontally negative 1, and then we would end up not traveling vertically. So we are in the real numbers here, which is why we can write real numbers as a complex number, and why real numbers exist in the complex plane. Let's try negative I. So if I were to do negative I, the real component is 0, imaginary component is negative 1. And if I were to plot this in the complex plane, I would be down here on the complex or the vertical axis. And let's try positive 1. So positive 1, I have 1 plus 0i. This means I will be here on the right side. So if I think about these 4 points that I just plotted, you should see a relationship. If we think about I to the power of 1, that's just going to be I, which is negative, which will be here. I'm sorry, not there. We're going up 1. And then if I do I squared, that is going to give us negative 1, which means our point will be here. And if I were to draw a curve connecting these 2 points, it would look like this. If we continue to I cubed is just negative I, so I would plot the point here, and again, I can continue this curve in this direction. And I to the 4th, that will be positive 1, and then I can connect the curve here. And if I do one more I to the 5th, that's just going to reset and be I, so we're back up here. Oops. So if we think about this figure here, if I were to continue I to the 6th, I to the 7th, it would continue and it would go on to infinity. So we have an infinite number of rotations here, but it's not just any type of rotation. If we think about this, we have a length here of 1, there's a length here of 1, and we have a circle, right? This is our unit circle. All right, so the unit circle does in fact exist in the complex plane. All right, and because of that, we can also think of these as angles. So if I have I can think of the corresponding angle as being pi over 2. And then if I have -1, I can think of the corresponding angle as being pi. For -I can think of 3 pi over 2. And then for 1, I can think of 0. Typically, we're going to work from 0 to 2 pi, non-inclusive for 2 pi, or 0 to 360, non-inclusive 360. All right, and this is why up here we see that we are dealing with the radius and we have a circle. Now, we're not always going to be dealing with a unit circle. The radius is going to fluctuate. It's going to change, all right? But we are able to find the radius using our beloved Pythagorean theorem, okay? Because we have a horizontal component and we have a vertical component. So we can also use this in the complex plane. So to find the radius, it's the absolute value of a complex number, and it's the distance from the origin on the complex number plane. So from the origin of the complex plane to the point or that complex value in the complex plane, we are able to find the radius using the absolute value. Now, the absolute value is going to be your magnitude or the length, right? This is, if you're in physics, you've definitely seen this. So that's the distance or the length. All of these are synonymous. But to find magnitude, you can use the distance formula, which is the Pythagorean theorem. Distance formula is x1 minus x2 or vice versa. However, because one of our points is 0, 0, we end up just using the complex number itself. So from here, if we want to find the radius, we have 2 plus 3i. Right? We are finding the radius is the magnitude of this complex value. Okay, so we can plug it into the Pythagorean theorem. The horizontal value is 2 squared, and then the vertical value is 3. Now we're in the complex plane. I know that it's 3i, but that I is just to specify that that is the imaginary component. The actual length of that, or the distance traveled, is just 3. So we do not include the I inside of our Pythagorean theorem. And we get a radius of root 13. Now, some other notation that you may run into is that to write a complex number, we can represent that with the letter z. All right, and now since this is the radius, we technically found the magnitude of this complex number. So this is the absolute value of z. So z is technically equal to a plus bi. So you're going to see that thrown around quite a bit. So that way you're used to that. All right, so next page. Now we're going to be looking at the trig form of a complex number. So we're shifting over to what we kind of talked about the last few units in semester 2. So trig form of a complex number is written like this, and I'll talk about where that comes from. But the first thing you need to be comfortable with is that r is the distance. R is the distance from the origin to point P, all right? So from the origin to point P. So that will be here, this is the origin, and then this is our point P. Now, if we look at this, we do have the unit circle here because the radius is 1. Anytime you hear a unit, that means 1, okay, or unity, 1. Now, if I were to take my unit circle, and we are leaving the realm of the unit circle, we are going to blow this circle up, and it's going to have a radius of 5. Now, what you notice, or should notice, is that we had a square root of 3 over 2, and then 1 over 2. Now, because the circle is 5 times bigger, that means your coordinate point is going to be 5 times the distance from the origin. All right, so now from the origin to my point P, my coordinate points are being multiplied by 5, all right, because radius is equal to 5. So if we bring it back, talk about the unit circle again, this is where we talk about our angles, okay? The angle is always coming from the center or the origin. Now, what you'll notice here is that these are similar triangles, right? The sides are different, but from here, these angles will be the same. It's a 90-degree triangle, 90-degree triangle. Now, even though we're blowing up that right triangle, the angle theta does not change, all right? As long as we have this point P out here and they have the same relationship or the same ratio, that theta will be the same, okay? So in the complex plane, A is equal to cosine theta, B is equal to sine theta. Now that's for the unit circle. So that means 1 and 1, okay? If we think about in the Cartesian plane, it was x is cosine, cosine, and then y is sine, right? So we have that horizontal relationship and that vertical relationship. So going back to rectangular form, if you think about rectangular form is a plus bi. We have our real component, and then we have our imaginary component. And the real component is horizontal, so that means that's going to be your cosine. The imaginary component is vertical, so that will be your sine, okay? So that's why they align here as A will be cosine theta, and then B will be sine theta. And then we will have that imaginary component. And this is your trig form, almost, okay? Now for trig form, you need to multiply the trig with the modulus of z, and z being your complex number. So you need to multiply the trig with the modulus of z, which is r. So that means we have a is equal to r cosine theta, and b is equal to r sine theta. So if you look at this up top, we can see that in our unit circle, we have root 3 over 2 and 1/2. That's because the radius is 1, but we are technically multiplying those with 1. And then if you look at the larger circle over here with the radius of 5, we have the same coordinate points, but they are both multiplied with 5 because that's how much further they are from the origin. So we have to multiply it with the length of the radius, okay? And you have been doing this with the unit circle, but because the radius is 1, we don't include it. But now that we will be dealing with multiple different types of circles with any number of radii, we have to include that r in this now. So this is one of the most important things that you will learn in this course, because you're going to take it with you for the rest of the year, and you're also going to take it with you to next year for calculus, okay? So trig form, or all of these equivalencies. So we have z, that is your complex number. Our rectangular form is a plus bi, okay? Now, if we want to rewrite this in trig form, a is going to be r cosine theta, b will be r sine theta. So we will have ri sine theta. And there is a shorter way to write this. They both have r in common, so I'm going to factor that out. So I have cosine theta plus I sine theta. And from here, we can even shorten it even more. And what we're going to do for the rest of this course is we will see r cis theta. Okay, so we have our radius here. We have cosine here. We have the imaginary component. We have sine. And then both of your thetas are represented here. These thetas will always be the same, okay? They will always be the same. And it's because of this conversion here from the unit circle all the way from rectangular form that they will be the same, right? It's because of the relationship that they have from the unit circle, alrighty? So this is your radius, and this is your angle. And in the next video, we will talk about converting from rectangular to trig and vice versa. So this will be very important to understand. All right, hope this helps.